Hey everyone, in the last video we saw about how we could think about the behavior of individual particles in order to build a model for the bond energy of a substance. In particular, we found that if we know the amount of energy in each bond, and then we just add that up for all of the bonds in our substance, then we can get the total bond energy. So you might think that we could do the same thing for thermal energy. Why don't we just find a way to determine how much thermal energy each particle in our substance has and multiply that by the number of particles in a substance? Problem solved. And you would be right. That is the approach that we're going to take. But the first part of this model turns out to be a little bit tricky. Finding the amount of thermal energy held by each particle is not as simple as it sounds. In a moment, we're going to go to the whiteboard and think about what this means. But let me give you a little preview. We know that the amount of bond energy for a single pair of particles is just given by the amount of potential energy that the particles have when their temperature is zero. We found that at zero temperature, the particles will just settle down into the lowest part of the Lennard-Jones potential, because that's the only place where they can sit and just not move. But what happens when we start adding energy to the system? Well, when we add energy to the system, the particles will start moving. They now have potential energy as well as kinetic energy. But the particulars of how they move turns out to be a little bit interesting. And that's going to allow us to figure out exactly how bond energy and thermal energy are related to kinetic and potential energy. Let's go to the whiteboard. So here we are, back at the Lennard-Jones potential. We're here because the Lennard-Jones potential just shows up everywhere when you're thinking about how individual particles behave. Now, the goal is, of course, to build a model that describes how thermal energy works for a very large number of particles, so that we don't actually have to think very much about the Lennard-Jones potential. But we still have to start here. So let's start where we left off with bond energy. Specifically, let's just imagine that we have two particles that are sitting right at the bottom of this well. In other words, they're the equilibrium distance apart, and they have zero kinetic energy. Now let's add some kinetic energy to the particles. And let's actually add a specific amount. Let's add 0.2 epsilon of kinetic energy. Well, what will the particles do now? Well, let's just think about the total energy of our system. Originally, our particles just had potential energy, and we know exactly how much they had, negative epsilon. So what is the total energy of the particles now? Well, it's just negative epsilon plus 0.2 epsilon. That adds up to a total of negative 0.8 epsilon. So we know that the total energy of our particles is negative 0.8 epsilon. I'm just going to mark that on our graph with a line. So what are the particles going to do now? You can basically sort of imagine that they're just connected by a spring. We've given the spring some energy and then just let it go. So they're just going to sort of bounce back and forth forever. As they move back and forth, they're constantly going to be exchanging their kinetic energy for their potential energy. When their potential energy goes down, their kinetic energy will go up, and when their kinetic energy goes up, the potential energy will go down. They'll keep doing this forever unless some energy is later taken out of the system. Whenever particles are bonded together but are bouncing back and forth, they have thermal energy. But how much thermal energy do they have? Well, the answer might not surprise you. They have 0.2 epsilon of thermal energy. Remember that bond energy only changes when a phase changes. Well, I never really explicitly said that the phase of this substance isn't changing. I'm going to tell you now. The phase of these two particles is not changing. They're still a solid. And so the bond energy is still negative epsilon. Well, perhaps you're a little bit confused now. The potential energy of the particles is always changing. That's what I just said. They're bouncing back and forth, exchanging potential energy for kinetic energy and back. This is true, but remember how we defined bond energy. We said that the bond energy of a pair of particles was equal to the amount of energy that they had when the particles were at zero temperature. That amount is negative epsilon. It's just the potential energy between the particles. And so our bond energy is just going to stay like that until a phase change happens. But because the total potential energy of the particles is just changing all the time, we can't just say that the bond energy is equal to potential energy and the thermal energy is equal to kinetic energy. So what can we say? let's ask a question that we haven't really asked in this course. If you have a mass attached to a spring and it's allowed to bounce back and forth, how much kinetic energy and potential energy will it have on average? What we mean by saying on average is just saying, let's allow the spring to bounce for a very long period of time and track how much kinetic energy and how much potential energy it has at all those times. We're not actually going to derive this in this course. It's not super interesting. But it turns out that when you do this exercise, you end up with, well, half. Half goes into each. In other words, over a long period of time for a spring mass system, half of the energy that the system has will be in its potential energy, and half will be in its kinetic energy. It turns out that this applies to these particles too. Remember that when we got started, the particles weren't moving. They were just sort of sitting down here at the bottom of the well. When we gave them energy, they started bouncing back and forth, constantly trading their potential energy for kinetic energy and then back. So the question we might ask is, how much of that energy that we added on average ends up in the kinetic energy of the particles, and how much ends up in the potential energy? The answer is exactly half. Again, on average, over a long period of time, half of the energy that we add to the particles will be in their potential energy, and half will be in their kinetic energy. So the bond energy of the particles has increased, right? Their potential energy has increased. Well, not so fast. Remember that we said that bond energy only increases when a substance changes its phase. This is still true here. And it turns out that for this example, the particles are not changing phase. They're still a solid. So we're saying their potential energy increased, but their bond energy didn't. How is that possible? Well, because of the way that we defined bond energy. We said that bond energy is just the amount of energy that particles have when they're at 0 degrees Kelvin. That energy is all potential energy because that's the only kind of energy that particles have when they're not moving. But once thermal energy comes into the picture, things get a little more complicated. It turns out that thermal energy is split between potential energy and kinetic energy, whereas bond energy is just potential energy. So, how much bond energy do these particles have at this moment? Well, it's the same amount that they started with. The bond energy hasn't changed because the particles haven't changed phase. So the amount of bond energy that these particles have is still equal to negative epsilon. All of this energy, all the bond energy, is potential energy. What about the thermal energy? Well, the thermal energy is just equal to the amount of energy that we added to the particles, 0.2 epsilon. But in this case, the energy gets evenly split between potential energy and kinetic energy. So it turns out that the bond energy of particles and the potential energy of particles is only the same when the particles have no thermal energy. As soon as we add thermal energy to the particles, the potential energy changes, even though the bond energy is staying the same. So how much potential energy do these particles actually have? Well, there are two sources of potential energy here. Their bond energy and their thermal energy. They have negative epsilon of potential energy from their bond energy and 0.1 epsilon of potential energy from their thermal energy. So the total amount of potential energy these particles have is negative 0.9. And the total amount of kinetic energy these particles have is 0.1. So what's their total energy? Well, we know it should be equal to negative 0.8 epsilon. That's what we already found. If we add up the total potential energy and the total kinetic energy, we get negative 0.9 epsilon plus 0.1 epsilon, which is equal to negative 0.8 epsilon, as we expect. Similarly, if we add up the thermal energy and the bond energy, we get negative epsilon, that's how much bond energy we have, plus 0.2 epsilon, that's how much thermal energy we have. This also adds up to negative 0.8 epsilon. But again, bond energy is not exactly equal to potential energy. The energy that we add as thermal energy gets split in interesting ways. And so the bond energy is only equal to the potential energy when the particles have no thermal energy. We can write this out in a couple of nice little equations. This equation just says that the total potential energy of the pair of particles is equal to the bond energy of the particles plus 1/2 of the thermal energy, and the kinetic energy of the particles is equal to the other half of the thermal energy. Now, okay, this is great, but why is this? Well, the answer to that question is going to take us a little bit longer to work out. We'll see it in the next video and the next DL. But the key thing that I want us to take away is that kinetic energy and thermal energy are not the same thing when you're talking about particles. They're related, of course. The kinetic energy of the particles depends only on how much thermal energy they have. But that's not the whole story. When we add thermal energy to particles, when we increase their temperature, that energy we added gets split evenly between the potential energy of the particles and the kinetic energy of the particles. Both their potential energy and their kinetic energy are increasing as we add energy. But their bond energy is still the same. It's just the potential energy that the particles had when they were at zero temperature. Now, this model actually turns out to be only true for solids and liquids. For gases, things change, and we do not have the time to talk about that right now. But I'll give you a little preview of what's coming. What we're going to find is that the amount of thermal energy that a particle can have depends on this thing called the number of modes that the particle has. You can think of a mode as just being a box that thermal energy can go into. When you have a solid, there are two kinds of boxes available. Half of the boxes for the particle are kinetic energy boxes, while half of the boxes for the particle are potential energy boxes. When you add thermal energy to the system, it gets split evenly between all the boxes. And so you end up with half of your energy as potential energy and half of your energy as kinetic energy. If we can determine how many boxes a particle has, we can figure out how it's going to behave as we add thermal energy and, well, how much its temperature will change. We don't have time to do that now, but we'll see it in the next one.